Following presentation is the first in what I hope will be a series of presentations on my independent study on the subject of transcendental phenomenology, I guess is as good a term as any for referring to investigating independent research of one's own based on experience of life. It is under the featured under Meditations on the Essential Trigon. This is the second contemplation of that series. Contemplation 2, the appearance of physical phenomena. I also have, or will have, some coming out that cover simple harmonic motion in a little greater detail to show that that's essentially what fundamental particles are resonant and driven versions of, as I understand those terms, of rest mass as simple harmonic oscillations. So in this case, it's baryonic rest mass as an emergent function of the Hubble rate. And the full development of this is shown in the related or the linked books. Go into the necessary detail, mathematical detail, for explaining that the rest mass is a function of the Hubble rate. And because rest mass comes before light and photonic energy, it's really the basis of all material quantum forms and material fundamental forms that we encounter. The other three areas that I am trying to include as part of this overall meditation is contemplation 1 is a life of essential principles, and deals with the concept of intentionality as a necessary part of material inertial reality. And also contemplation 3, which is the quality of political economy in this case, but it's quality of all social knowledge and interactions. And we'll get into discussion of our presentation of Platonic or Plato's Republic in terms of the inertial trigon. The inertial trigon is essentially, the concept is that anything that shows up or appears to the senses is a result of three fundamental essential capacities. One is the inertial capacity of material nature, the other is the intentional capacity of spiritual nature, and the third is the formal capacity of ideal nature, which is the mental concept, and fills in most of all the forms that span the spectrum from an inertial end to one end of material nature to the intentional end, completely intentional end of spiritual nature. And those three form the three sides of the triangle. The field that makes the triangle a trigon as a polygonal form is the fourth principle, and that is the imaging capacity of soul natures, and is a necessary and equal part to the other three principles in my conception, which is responsible for for basically carrying out in detail all the functional intent of the intentional or purposeful aspect of life, which is generally referred to in most religions as the paternal aspect. The maternal aspect, which is missing in so much of Christianity, unfortunately, is the inertial aspect, the material aspect of life itself, which is equal to the paternal. It's just viewed a little differently, I guess. So that's where we're going with this. I hope you enjoyed it. The following is a model of expansion stress on a unit space, which I'm calling by the acronym IESUS, as a model of baryonic generation, emergent baryonic generation from expansion of a space-time fabric localized in the galactic webs. The following it's a graphic development of baryonic matter observed in all material interactions as the emergent quantum function of observed global expansion stress on a local isotropic space, for which I'm using the acronym IESUS, a torsional classical wave analysis. Full development of the model can be found in the various monographs found on the uniservant.org website and in the related Uniservant publication. The tome is entitled Unification in Physics and Political Economy by Martin Gibson. It's available in the independent bookstores and on Amazon and online in general, in hardback and paperback version. It's pretty hefty, but I think you'll get some insights out of it, perhaps. I certainly hope so. Thank you and enjoy. Here we have a representation space for modeling the effect of isotropic expansion stress on a local unit sphere. The inner sphere is a boundary to local observable differential inertial change. Effectively, it serves as a quantum event horizon. The outer two sphere is a boundary to external global effects other than those that are modeled here. And that represents effectively a ergosphere if we were to use a extreme Kerr metric to model this. Which is actually a wave model. But the assumption is that we know nothing about the interior of this space here other than the fact that it exhibits classical inertial response to rotation and translation impulse. The local sphere is assumed to be embedded in a global continuum, obvious continuum conditions are held to exist. Here we have a slice through an arbitrary XY plane. The red diagonals are embedding references for, as we shall see, uh, unit coordinates that are equally uh, uh, equidistant from the unit coordinates, which are shown here. The assumption is that these coordinates, we're using the subalt for, as here, subalt y, subalt x, subalt minus y, subalt minus x are on the surface of this unit sphere, and they take their initial in the initial condition, they take this reference from the larger axial point shown here, x and y. The rotation, axial rotation, is shown at the center by the dot on the left-hand side, which represents the an axial vector pointing out of the page. All of these use the right-hand rule. And the circle on the on the right-hand side shows the shows a right-hand vector pointing into the page, as shown by these circular or angle vectors. The unit boundary acts as a ceiling of maximum density, engaging the generation of rest mass particles from a lattice potential of what is a 3D continuum of variable flexible density stress. There are no particles of rest mass or energy transfer of a separable nature in this modeling. All discretations, we might call it, are understood to be torsional wave formations of the continuum. Energy, discrete or continuous, is classically understood as a quantifiable potential to produce change or to register actual change in the field of observation, including as a variable inertial density of spacetime itself. That spacetime is modeled orthogonally using conventional XYZ orientations using the right-hand rule. De Sitter and anti-de Sitter space can be modeled as an emergent feature of this setup. The Hubble rate gauges time and not the speed of light, as in Minkowski spacetime. Dark matter is the entrained material of the interface dynamics, which occurs between the inner and outer boundary, where the dynamics that produce spin and electromagnetic, quantum electromagnetic fields and gravity are generated by this action. In the prior slide, the coordinate designations such as x subalt and xy subalt are considered unit labels applying to the unit sphere, inherited from the potential of an XYZ global system as an initial condition prior to active modeling effects. As those effects evolve with rotation of the unit, the labels, as seen in the prior slide in standard font style, rotate with the unit as snapshots in time. Those same labels are shown italicized with a sawtooth underline to distinguish them as initial positions with respect to XYZ in equilibrium, as time exposures, to indicate any displacement through those initial positions by any such rotating label. Such initial positioned labels, while so placed, will be in standard font bold with a sawtooth underline. Here viewed from the y plus y axis toward the y or towards the xz plane, x and z represent arbitrary axes orthogonal to each other, as do the diagonal reference lines in a plane. In an initial condition of a field in which they are inertial and isotropic prior to expansion stress, by which we will induce torsion. Here, x and z represent arbitrary axes orthogonal to each other. In an initial condition of an inertial field that is isotropic prior to expansion stress, which has induced torsion. Such expansion stress might be modeled as a gradient normal to or along the interface between regions of sufficient density differential. The interface strain is represented by 8 radial displacements as rotation of the unit sphere, where the strain is assumed to be uniformly distributed in the bulk about the inner circle in response to an effective isotropic differential stress in the xz plane. The outer circle is assumed stationary, while the area inside the circle undergoes torsional strain displacement. The inner circle represents the boundary of maximum displacement along each radial line as a coordinate singularity, which gauges the unit radius x equals z equals 1. Here is a rotation of 1/4 pi. The small disk at the center indicates an axial vector pointed toward the viewer according to the right-hand rule. At a maximum sustained stress, the rotational strain is stopped, as indicated by the removal of the angular arrows and the central directional hub of the axial vector. Those arrows represent an integral of the forces as a torque over each entire 1/4 pi rotational arc. But it must be understood that such forces are not instantly applied. Over time, they accelerate differentially from 0 to some finite speed and then decrease to 0 as the maximum strain is reached. The strain is still indicated here under conditions of elasticity, which assume an absence of material fatigue, but retain the potential for hystereses. The torsion stress remains, though the rotation has stopped. If that torsion stress is diminished from factors beyond the outer boundary, a recoil of the strains will occur. Otherwise, increased differential stress beyond a theoretical maximum is directed into the y hemisphere on either side of the plane shown. With the removal or diversion of the initiating torsion stress external to the outer boundary, we can see that the element of torsion stress which has been induced into the tension strain remains as indicated by the lengthening of each initial radius in the interface. Note the radii on the interior of the unit sphere remain unchanged, so that elasticity conditions work to shorten each line towards its initial length. As this recoil begins, again with a differential acceleration from 0 towards some maximum, the arrows in the axial hub have reversed their direction as indicated. Here we have a view of the initial torsion viewed from the plus z axis. The y-axis of torsion stress and strain is represented as an axial vector by the right-hand rule pointing to the left as the stress and strain increases, and to the right during the recoil cycle as those factors decrease. Here the locus of maximum and region of greater stress strain is in the XZ plane, circling the unit sphere, shown after a 1/4 pi rotation as viewed from the plus Z axis of the previous slide. The regions of lesser torsion strain on either side of the unit trail off in intensity toward the outer interface boundary. If the stress is removed from this point, it becomes an inflection moment of maximum strain and the commencement of recoil. Effectively, as the moment is approached, the intensity of the arrow in Y will vanish as the arrow of minus Y begins to appear. Next, we have a recoil of torsion to equilibrium viewed from the plus Y axis. In the absence of a sustained restraining torque in a condition of elasticity, the torsion strain recoils to its equilibrium condition, indicated by the return of the lines in the interface area between the circles to their initial condition, and according to the font style designation for all positions. Here we have a view of oscillation of torsion phi in dynamic equilibrium from the plus Y axis. If this represented an instance of a torsion pendulum, at this point the momentum and the recoil strain would continue as shown in the clockwise direction before reaching maximum strain and recoiling once again. Under ideal conditions, the process of oscillation will continue indefinitely as an instance of simple harmonic motion. Note that we have changed the color of the rotation arrows once again to red to indicate the areas of the unit sphere are moving in a direction of increasing stress and therefore increasing potential energy and mechanical charge, providing recoil capacity. Here we have oscillation of torsion phi shown with reflected phasing. With a split screen approach and initial labels retained, assuming a torsion oscillation involving a 1/2 pi strain in each direction, from 1 at Z equals Z sub alt, we can depict 8 stages of each oscillation. These consist of the 2 predominant qualitative states, potential energy capacitance, shown with the red arrows, and kinetic energy inductance, shown with the gold arrows, each of which has 2 first-order geometric directions, positive and negative. Each of these 4 has 2 second-order intensities, increasing and decreasing. That oscillation can be represented with a type of phasing from 1 to 8 for each cycle. Note that at the reflection plane represented by the x-axis, the line between phase 2 and 3 and 6 and 7 represents a flipping in the torsion rotation of phi as a right-hand axial vector. Such flipping is a stop reverse flip and not a body flip phenomena. Here we show the moments of maximum energy conversion. With a bit of foresight, we can see the symmetry in this view in the manner of a phase space chart of simple harmonic motion or uniform circular motion with respect to one axis, by removing the stipulation that the 2 sides of the chart are reflections as half cycles. In this case, the x-axis represents displacement of a body with a maximum of plus or minus x sub alt, and the z-axis represents the body's maximum momentum at plus or minus z sub alt. Without further detail, we do this to point out an important feature on the space charts we have been investigating concerning the points of maximum efficiency in conversion of momentum to displacement in the cyclic storage of potential energy at plus and minus E, and of the reverse in maximum conversion of displacement to momentum plus and minus M. From our modeling, we see that this corresponds with the diagonal reference lines of the unit sphere at x, z sub alt minus x minus z sub alt for E, and minus x z sub alt x minus z sub alt for M. Here we have an example of the extent of torsion phi about the y-axis as viewed from the plus y-axis. Returning to our initial view, adding strain vectors other than the four radials from the two designated principal axes to indicate the isotropic nature of the expansion stress, and continuing the rotation to 1/2 pi at some point between the 1/4 pi and 1/2 pi rotation, indicated by the red lines, dependent on the flexibility of the medium indicated by the distance in the interface between the circles. The strain begins to compress the inner circle and or offer increasing resistance to the torsion strain. As the strain length between the unit and the boundary circle increases, where the cosine of an angle such as z sub alt, I can't read this very well, z sub alt, and initial z sub alt approaches 1, the differential effect of the torsion compression stress on the unit circle increases proportionally. We have a symmetry break in torsion phi recoil viewed from the plus z axis. From a previous slide, maximum strain is assumed in the interface with the plus or minus z sub alt strains, ideally aligned with the x-axis, forming a torus around the y-axis to either side of the xz plane, adjacent to the unisphere as indicated in red. Regions of lesser strain are indicated adjacent in gold. Sustained torsion of expansion stress prevents direct recoil in the xz plane, arresting rotation about the y-axis. Any differential energy is directed from the xz into the adjacent hemispheres to left and right. The symmetry break from phi recoil about y results in rotation about the x, y, and z axis. Per the angular arrows, as the differential recoil of z sub alt to minus z sub alt moves counterclockwise about the minus y and plus z axes towards the diagonal moments, plus and minus m in opposing hemispheres xz or yz and minus y minus z move toward their initial positions in the yz plane, pulling plus minus e toward x sub alt minus x sub alt, rotating minus x sub alt and x sub alt about x plus x. This sets up sustained oscillation of the unit y sub alt z sub alt great circle through the x sub alt to minus x sub alt poles, the x-axis, while the x minus x sub alt to x sub alt sustained maximum strain rotates in the unit y z great circle, avoiding coordinate entanglement condition. Boy, that's a mouthful. Again, we look at the symmetry break in phi torsion recoil from the plus x-axis. The initial rotational strain about y having reached its limit, a break in symmetry is made as z sub alt moves towards minus m and z sub alt towards plus m, not visible. Plus E moves towards z sub alt and minus E towards minus z. with a rotation which is not visible, with a rotation as a reemergence of phi around the z-axis. That recoil moves m toward xz in an inductive or kinetic energy phase, having moved minus yz to E as part of a capacitive or potential energy charging phase with the initial strain. The minus x hemisphere likewise. This moves z sub alt to an initial position at x, y, z sub alt, and of minus yz sub alt to the position currently held by z sub alt at x sub alt, while minus y moves to x minus y minus z sub alt, and y sub alt moves to minus x, y, z sub alt. This symmetrical recoil initiates a sustained theta rotation about the x-axis as x sub theta, while minus x sub alt, x sub alt rotates as phi, initially from the plus z-axis. As a result, the sustained stress as potential energy capacitance charge, shown in red, becomes localized in the polar regions of the emergent theta rotation, while the kinetic energy reductance as a sustained circulating oscillation of phi as a wave force forms a torus around the x-axis as shown in gold. In an emergence of theta and phi about x and about the minus x sub alt, x sub alt displaced or strained axis. Over the course of this rotational oscillation, we start with recoil from the position of the initial torsion displacement strain, and thereafter for successive oscillations through phase 1 and 2. Based on a right-hand rotation starting about the z-axis, z sub alt shows oscillation, shown oscillates as points 3, 4, 5, 6, 7, 8 to complete the cycle at 2, forming a figure 8, all within the z hemisphere. Simultaneously, at the other end of the strain, in the minus z hemisphere, minus z sub alt completes the reverse of this path, starting at 6 through, but not shown, 7, 8, 1, 2, 3, 4, 5, to complete the cycle at 6. The result of this rotational oscillation is a redirection of sustained strain as potential energy and charge capacitance, pictured in red from the prior slide, into the polar regions of this one, and a marked enlargement of gold regions of less stress along the y-axis to the kinetic energy and inductance about the middle region of this, essentially depicting the sustained transfer of the potential stress energy density of the global continuum to this quantum kinetic energy. This produces a cycle of effective rotation of x sub theta, and the strain, displaced strain x to minus x rotation as shown. The above magnetic induction and electrical charge moments, M and E, are taken from a prior slide on the 8 phases of the oscillatory cycle and reflect the phase transitions of those torsional strains. As there stated, the 4 moments are the points of transition between predominant states of potential and kinetic energy, capacitance, and inductance for both directions of travel. Those moments have been transposed in the bottom of the diagram, however, due to the effective synchronized rotation of x sub theta and minus x, which places both induction moments on the transition side of the potential energy to kinetic energy, and the capacitance moments on the reverse side of the kinetic energy to potential energy. The current strain, phase 2, shown is a maximum displacement and stress of z sub alt to x sub alt, and the corollary of minus z sub alt to minus x sub alt. The relevant moments currently shown in the xy plane rotate continuously in that relative position on the unit ball within the unit sphere. Here we have a look at the capacitive and inductive torque cycle about x sub theta and x sub alt minus x sub alt axes. Here we have a representation of the YZ plane of the unit sphere after initial torsional displacement as as phi, about y, viewed initially from the z-axis. In the process of that displacement, according to the right-hand rotation of the axial vector at z by 1/2 pi, the 4 diagonal points on the circle are positioned on the 4 moments of prior slides. These effectively produce 2 cross products of these 4 displacement strains as shown, resulting in 2 duplicate torques, one inductive torque for the plus or minus m at the induction torque, and one capacitive torque for the plus or minus E at the C, the capacitive torque, as indicated above. Once recoil rotation emerges, L and C align with 2 of the diagonals of the unit cube in a superposition of the unit sphere and rotate in that position about the x sub alt axis. Note that the plus m and minus e moments transpose on the lower half from the prior slide due to the synchronous rotation of theta and phi, while the emergence of the unit sphere from analysis of a global isotropic strain can represent a function of a de Sitter space, a conformal system of pseudospheres on the rotating 8 diagonals provides a model basis for anti-de Sitter space. And now we get to the meat of the matter. What we have with these circulating torques is a neutron as an effective rotation of phi about theta, viewed from the plus z-axis. While phi torsion recoil from the driving effects of a sustained expansion stress is responsible for the dynamic of the unit sphere, they can be represented and understood as the emerged and sustained rotation of a capacitive and inductive torque that drive the oscillation as the fundamental properties of rest mass, spin angular momentum, electromagnetic interaction, and quantum gravity. This view represents this dynamic as the neutron, where the effective spin moment and the counter directional magnetic moment of the quantum particle are defined deterministically using classical wave mechanics elsewhere as an emergent function of expansion stress, observed and currently recognized as the Hubble rate. The numbered legend, each of the 1/4 pi duration of theta, indicates the path followed, here as an initial position of z sub alt as phi oscillates. After a few minutes, that state decays as follows, and that is approximately 13 minutes, something like that. Next, we have the proton as an advanced rotation of phi about theta, viewed again from the plus z axis. In an environment of sustained expansion stress on a free neutron, the induced rotation speed of theta from the inductive torque advances the phasing of phi by 1/2 pi, and the induction torque drops as shown, emitting the energy of an electron and related neutrino phenomena of beta decay in the process, as indicated by the inductive torque. To complete the picture of baryonic generation, we have an antiproton as a retarded rotation of phi about theta, once again from the plus z axis. In an environment which mitigates sustained expansion stress on a free neutron, the induced rotation speed of theta from the capacitive torque retards the phasing of phi by 1/2 pi, and the capacitive torque drops as shown. The reason for the general lack of antiprotons in an environment of general expansion stress and strain is apparent from this modeling. A full development of this subject is available in the monographs of uniservant.org as Unification in Physics and Political Economy by Mark Gibson, as shown here. The ISB numbers are shown. Inquiry is welcome, and we're open to any discussion and feedback. Thank you for your time. In conclusion, as a postscript, I thought these three equations, which relate to the development of this slide presentation, offer verification of this line of thinking. General relativity. In flat space-time, absent mass or energy quanta, the field equation on the left is reduced so that the stress energy density is a function of the cosmological constant, lambda, as the Hubble rate in this thinking, and the Einstein tensor, here seen as a gauging metric, to produce the time-free rest mass tensor 2T. With respect to Newton, as a statement of Newton's gravitational law in quantum form, tau sub 0 g is a quantum of gravitational force, shown in the last form to be the trace components of a wave force differential with respect to a change in stress, delta t. It's important to understand that the quantum of force doesn't mean it's a discrete bit of data, so to speak. It is an invariant given this situation or this development. As far as quantum field theory, the 18 gauge components, tau sub ij of the tensor T, are shown in a double or isometric matrix 2T as the 6 gravitational trace components, delta T or delta tau, and 12 rotating oscillational torsion components, tau sub alt, that produce quantum spin, angular momentum, and the quantum electromagnetic moments, torques, and fields. From an understanding of the relationship between a unit stress energy density, T sub alt, and each normal stress component on a unit cube, F sub alt, we have the following. Combined with Newton above, we can reduce G in quantum terms using the known values of Planck's reduced constant h bar and the speed of light c, where tau is the inertial constant of this modeling shown below as h bar divided by the speed of light. This gives us the following expression of G. We know G, we know tau, and from that we can solve for r to the 6 and find out what that represents as a gauging value. And so we solved to find the gauge value of r sub alt as shown, which is the reduced Compton wavelength of the neutron, along with the remaining values developed in this model and confirmed by well-known experimental data in the ratio of the strong force tau sub alt to the gravitational differential of d tau. And we get the following values. Well, that ratio is 10 to the 38, which is in line with the established body of knowledge. This means that the wave force of the the wave force of the neutron is 7.16 times 10 to the 5th newtons on each, in this case, a neutron. Proton will be a little bit less. So there you have it. I hope someone will study this and see how correct it is. Thank you. One final bit of information worth mentioning is that the Hubble rate is actually gauged by the wave force of an electron, which is in the neighborhood. It's right around I think a little bit less than 1 Newton, and so if we divide that by the speed of light, we arrive at a number which is the Hubble rate. And what this indicates is that the expansion, the Hubble rate, drives this oscillation over time, and it's responsible for the decay, for beta decay, and for generation of the electron from expansion. Thank you very much. Linked references in the second section of the chapters on Contemplation 2 and 3 are to monographs related to modeling a physical theory, 7 of those, and investigative political economy, 3. These have been compiled together this year under a separate title as Unification in Physics and Political Economy, subtitled by an introduction, The Aim and Goal of All Modeling, Clarity in Navigating Risk and Opportunity. These are offered in paperback and hardback version. The print versions are available through local bookstores and online, but the EPUB version is not available as of this time. With this reference made, we move on to the presentation of the Essential Trigon. Finally, we have some contact information if anyone is interested. Much of what is provided in the slide presentation can be found online in various forms at the website uniservant.org. Peace and love.